The process begins by examining the individual spatial components of two vectors. When we expand the squared magnitude of their cross product, we are left with a complex set of terms involving these components. The most elegant way to make sense of this complexity is through a mathematical bridge known as Lagrange's identity. This identity reveals a deep connection between the cross product and the dot product. Because the dot product is already known to relate to the cosine of the angle between two vectors, we can substitute that relationship into the identity. By applying the fundamental rule of geometry that links the squares of sine and cosine, the expression transforms to show that the magnitude of the cross product is directly dependent on the sine of the angle. This derivation results in a clear method for calculating the sine of the angle between any two vectors using only their Cartesian coordinates. By taking the ratio of the total magnitude of the cross product to the product of the two individual vector lengths, we can determine the exact angular relationship between them. This formula serves as a direct link between abstract spatial data and trigonometric reality. In the physical world, this mathematical structure is used to model phenomena that rely on perpendicular interaction. Two primary examples are magnetic force and torque. When a charged particle moves through a magnetic field, the force it experiences is not uniform. It changes based on the direction of travel. The force reaches its absolute maximum when the particle's velocity is perpendicular to the magnetic field. However, if the particle moves parallel to the field, the force disappears entirely. A similar logic applies to torque, which measures the twisting force applied to a lever. The rotational effect is at its peak when a force is applied at a right angle to the lever arm. If the force is applied parallel to the handle, no twisting occurs. These examples demonstrate that the cross product is the perfect tool for describing any system where the interaction is strongest when the two inputs are perpendicular to one another.